Hello there, and welcome. It's good to have you here. Perhaps you've had a long day, or maybe you're simply curious about the invisible threads that connect our world. Either way, tonight is for you. You have nothing to do but rest, to let your mind gently wander through the intricate systems that make the internet possible, to understand the quiet machinery that hums beneath every message sent, every video watched, every search completed. Tonight we're going to explore something you use every day but rarely see. The internet. Not the websites or apps you interact with, but the actual physical infrastructure, the cables and servers and switches, the protocols and systems that make it all work. We'll travel from the ocean floor to data centers, from fiber optic strands thinner than hair to massive undersea cables, from the router in your home to the vast networks that span continents. This isn't a story of excitement or drama. It's a story of patient engineering, of systems working quietly together, of light traveling through glass, and electricity following paths through copper and silicon. It's the story of how, when you press a key or tap a screen, information begins a journey through a network so vast and so carefully constructed that it touches every corner of the modern world. So settle in, let your breathing slow. And let's begin this gentle journey through the infrastructure of connection. At the heart of the internet lies something surprisingly simple and surprisingly ancient: glass. Not the thick, cloudy glass of old windows, but glass so pure, so perfectly clear, that light can travel through it for dozens of miles with barely any loss. This is optical fiber, and it forms the nervous system of our digital world. Imagine holding a single strand of this fiber. It would be thinner than a human hair, flexible enough to bend gently around your finger, and yet strong enough to carry the weight of billions of conversations, millions of videos, countless searches and messages and connections happening all at once. This tiny thread of glass is where the internet truly lives. The fiber itself is made of silica, which is essentially very pure sand that has been heated and drawn into long, continuous strands. The manufacturing process begins in a laboratory where technicians create what's called a preform. This preform is a thick rod of glass, perhaps an inch in diameter and several feet long, with layers of different types of glass carefully arranged inside it. Each layer has been precisely engineered to have specific optical properties, specific ways of bending and reflecting light. Once the preform is ready, it goes into a drawing tower, a tall furnace where it will be transformed. The top of the preform is heated to around 2,000 degrees Celsius, hot enough to soften the glass until it begins to flow like honey. As the glass softens, gravity pulls it downward, and a thin strand begins to emerge from the bottom of the preform. This strand is the optical fiber. Machines carefully control the speed at which the fiber is drawn, pulling it down through cooling zones where it solidifies into its final form. The process happens quickly, with the fiber moving at speeds of up to 60 feet per second, or about 40 miles per hour. But even at this speed, the fiber maintains its precise dimensions. It must be exactly the right diameter, down to measurements finer than a single wavelength of light. Too thick or too thin, and the light won't travel properly through it. The finished fiber has a structure like a cable within a cable. At the very center is the core, a cylinder of ultra-pure glass, typically 8 to 10 microns in diameter for single-mode fiber, or 50 to 62.5 microns for multimode fiber. To give you a sense of scale, a micron is 1/1000th of a millimeter. A human hair is about 70 microns thick, so the core of a single-mode fiber is more than 7 times thinner than a hair. Surrounding the core is another layer of glass called the cladding. The cladding is made of glass with a slightly different refractive index than the core. This difference is crucial because it creates what scientists call total internal reflection. When light traveling through the core tries to escape into the cladding, it instead bounces back into the core, like a ball bouncing off a wall. This bouncing continues down the entire length of the fiber, keeping the light contained within the core, no matter how many times the fiber bends or curves. Around the cladding comes a coating, typically made of acrylate polymer or polyimide. This coating is only a few microns thick, but it serves several important purposes. It protects the glass from moisture and physical damage. It provides a surface that can be gripped and handled without touching the delicate glass beneath. And it adds a tiny bit of flexibility, making the fiber easier to install and less likely to crack under stress. But a single fiber, even with its coating, is still incredibly fragile. To make it usable, manufacturers bundle multiple fibers together and surround them with additional protective layers. A typical fiber optic cable might contain anywhere from 2 fibers to several hundred, all running parallel to each other down the length of the cable. The fibers are usually arranged in ribbons, with 12 or 24 fibers lying flat next to each other and held together by a flexible material. These ribbons can be stacked on top of each other, so a cable with 144 fibers might contain 6 ribbons of 24 fibers each. The ribbons are often color-coded, with each ribbon having a different color, and each fiber within the ribbon marked with colored rings or stripes. This color coding makes it possible for technicians to identify individual fibers when they need to make connections or repairs. The bundle of fibers or ribbons sits inside a central tube, sometimes called the buffer tube. This tube is typically made of plastic and is filled with a gel or a dry material that protects the fibers from water. Water is one of the great enemies of fiber optic cable. Even a tiny amount of moisture can seep into the microscopic spaces within the cable structure, and over time, this moisture can cause the glass to degrade, a process called water tree formation. The gel or dry material in the buffer tube keeps moisture away from the fibers. Around the buffer tube come strength members. These are strands of aramid yarn, the same material used in bulletproof vests, or sometimes thin rods of fiberglass or steel. The strength members are what actually bear the weight and tension when the cable is being pulled through conduits or hung from poles. They prevent the pulling force from reaching the delicate glass fibers inside. Finally, the entire assembly is wrapped in an outer jacket, typically made of high-density polyethylene or polyvinyl chloride. This jacket comes in different varieties depending on where the cable will be installed. Indoor cables have thin jackets and are designed to be lightweight and flexible. Outdoor cables have thicker jackets that can withstand sunlight, temperature extremes, and physical abuse. Armored cables, which might be buried directly in the ground or installed in areas where rodents are a problem, have an additional layer of corrugated steel tape or steel wire wrapped around them beneath the outer jacket. The way light travels through this fiber is itself a quiet marvel of physics. When you want to send data through a fiber optic cable, you use a laser or a light-emitting diode to generate pulses of light. These pulses represent the ones and zeros of digital data. A pulse of light means a 1. The absence of light means a 0. By turning the light on and off billions of times per second, you can transmit enormous amounts of information. The light used in fiber optics is almost always infrared, with wavelengths between 1,260 and 1,675 nanometers. This is beyond the range of human vision, which is why you can't see the light traveling through a working fiber even if you look directly at the end of it. These infrared wavelengths were chosen carefully. At these specific wavelengths, the silica glass has its lowest absorption and scattering, meaning the light can travel the farthest before it becomes too weak to detect. There are two main types of fiber optic cable, and the difference between them lies in how the light travels through the core. In single-mode fiber, the core is so narrow that light can only travel in one path or mode, straight down the center of the fiber. This single path means that all the light pulses arrive at the other end at essentially the same time, which allows for very high speeds and very long distances. Single-mode fiber is what's used for long-distance telecommunications, for connecting cities and countries, for the backbone of the Internet. In multi-mode fiber, the core is wider, wide enough that light can bounce around inside it at various angles, creating multiple paths or modes for the light to follow. Some light rays travel straight down the middle. Others bounce off the walls of the core at steep angles, traveling a zigzag path. Because these different rays take slightly different amounts of time to reach the other end, the signal can become smeared or dispersed over long distances. This limits how far multi-mode fiber can effectively carry a signal, typically to a few hundred meters or perhaps a kilometer. But multi-mode fiber has advantages too. It's easier to work with, because the larger core makes it simpler to align connections, and it can use less expensive light sources. So multi-mode fiber is common for short runs within buildings, connecting floors or rooms in an office or data center. The installation of fiber optic cable is a careful process, whether it's being buried underground, hung from telephone poles, or laid inside the walls of a building. Underground installation often uses a technique called horizontal directional drilling, where a machine bores a path beneath roads or obstacles without having to dig a trench. The cable is pulled through the borehole as the drill bit is withdrawn. When cables are placed in existing conduits, technicians use cable pulling equipment that can carefully control the tension, ensuring it never exceeds the cable's rated pulling strength. Aerial installation, where the cable hangs from utility poles, requires support hardware to bear the cable's weight. Often, the cable is attached to a stronger messenger wire that runs between the poles, or the cable itself contains a steel strength member that can support its own weight. Technicians must ensure the cable has the right amount of sag between poles, enough that it won't be pulled too tightly when the temperature drops and the cable contracts, but not so much that it hangs too low or bounces in the wind. Inside buildings, fiber runs through cable trays or conduits in the walls and ceilings, eventually terminating in network rooms or equipment closets. The termination process, where the individual fibers are prepared and connected to equipment, requires great precision. The fiber must be carefully stripped of its coatings without scratching the glass. The end must be cleaved or cut to create a perfectly flat surface perpendicular to the fiber's length. This cleave must be clean and precise, with roughness measured in nanometers. Any imperfection will scatter the light and reduce the signal strength. Once cleaved, the fiber can be spliced to another fiber or fitted with a connector. Splicing is the process of permanently joining two fibers end to end. The most common method is fusion splicing, where the ends of both fibers are aligned perfectly and then heated with an electric arc until the glass melts and fuses together. A good fusion splice has almost no loss of signal. The light passes from one fiber to the next, as if they were a single continuous strand. Connectors, on the other hand, allow fibers to be connected and disconnected as needed. A fiber optic connector holds the fiber in precise alignment within a ferrule, a tiny ceramic or metal tube with a hole barely wider than the fiber itself. When two connectors mate together in an adapter, their ferrules press against each other, bringing the fiber ends within a few microns of touching. This small gap allows for some reflection and loss, which is why connectors typically have slightly higher loss than splices, but the convenience of being able to disconnect and reconnect is often worth this small trade-off. Different types of connectors have evolved for different applications. SC connectors use a push-pull coupling mechanism. LC connectors are smaller and use a latching mechanism similar to an RJ45 Ethernet connector. ST connectors use a bayonet-style twist lock. FC connectors, often used in laboratory settings, have a threaded coupling for extra stability. Each has its place in the ecosystem of fiber optic connections. The capacity of these fiber cables is staggering. A single pair of fibers, one for sending and one for receiving, can carry multiple terabits of data per second using a technology called dense wavelength division multiplexing, or DWDM. This technology works by sending multiple wavelengths of light through the same fiber simultaneously. Each wavelength carries its own independent data stream. Think of it like sending multiple colors of light through the same piece of glass, with each color carrying different information. Modern DWDM systems can multiplex 80 or more different wavelengths onto a single fiber, and some experimental systems have pushed this to over 150 wavelengths. The glass in these fibers is so pure that if you made an ocean of this glass, you could see the bottom even if it were miles deep. This purity is measured in decibels per kilometer, a measure of how much light is lost as it travels through the fiber. Modern fibers have losses as low as 0.15 decibels per kilometer at the optimal wavelengths. This means that after traveling through a kilometer of fiber, the light still retains about 97% of its original intensity. Even after 100 kilometers, more than 60 miles, a significant portion of the light remains. This purity and low loss make fiber optics ideal for long-distance communication. Unlike electrical signals in copper cables, which fade quickly and require frequent amplification, Light signals in fiber can travel vast distances before they need to be boosted. This is crucial for the Internet's infrastructure, where data often needs to traverse thousands of miles of cable. Around the world, there are millions of miles of fiber optic cable. Some is buried beneath city streets. Some hangs from utility poles in suburban neighborhoods. Some runs through the conduits and cable trays of office buildings and apartment complexes. And some, as we'll explore next, lies at the bottom of the ocean, connecting continents across thousands of miles of seabed. But all of it serves the same purpose: to carry light, and with that light, to carry the digital information that forms the backbone of our connected world. As you rest, imagine these tiny strands of glass, thinner than hairs, running beneath your feet, above your head, all around you. Imagine light traveling through them, bouncing along their length, carrying conversations and videos and messages and searches, billions upon billions of pulses of light each second, forming an invisible web that connects everyone and everything. It's a quiet infrastructure, working ceaselessly, rarely noticed, but absolutely essential to the modern world. If you were to drain all the water from the Earth's oceans, among the most striking things you would see, besides the dramatic undersea mountains and trenches, would be a network of cables crisscrossing the ocean floor. More than 450 submarine cables currently connect the continents, spanning over 850,000 miles in total length. These cables carry more than 99% of all intercontinental internet traffic. They are, quite literally, the backbone of the global internet. A submarine cable looks different from the fiber optic cables we just explored. It needs to be much stronger, much more heavily protected, because it will lie on the ocean floor for decades, facing pressures, currents, earthquakes, and the occasional curious shark or ship's anchor. Yet at its heart, it contains the same basic components: optical fibers carrying light. Let's start by understanding the cable's structure, working from the inside out. At the very center of a submarine cable lie the optical fibers themselves, typically anywhere from 4 to several dozen pairs of fibers. These are the same type of single-mode fiber used in terrestrial long-distance cables, with cores measured in microns and cladding that traps the light through total internal reflection. The fibers are arranged in bundles or ribbons and held within a steel tube or surrounded by steel wire, forming the cable's core. Around this core comes a layer of copper, usually a solid copper tube or a layer of copper wires. This copper serves two purposes. First, it provides additional mechanical strength, supporting the weight of the cable and protecting the delicate fibers from being crushed. Second, and perhaps more importantly, it carries electrical power. Out in the middle of the ocean, far from any shore, the optical signals traveling through the fibers need to be amplified periodically, typically every 50 to 100 kilometers. These amplifiers, called repeaters, need power to operate, and the copper conductor provides that power. The way this power system works is elegant in its simplicity. At one end of the cable, a shore station applies a high voltage, perhaps 10,000 volts or more, to the copper conductor. At the other end of the cable, another shore station applies an equal and opposite voltage, creating a potential difference that drives a current through the conductor. This current, typically around 1 ampere, flows down the cable, passing through each repeater along the way. The repeaters extract the power they need from this current, using it to amplify the optical signals passing through their section of the cable. This arrangement means all the repeaters in a cable are connected in series, like a string of lights on a Christmas tree. If one fails, the entire cable can go dark. To minimize this risk, repeaters are designed to be extremely reliable, with redundant components and fail-safe modes that allow signals to pass through, even if the amplification fails. Around the copper conductor comes a layer of insulation, typically made of high-density polyethylene. This insulation must be thick enough to prevent the high voltage on the copper from leaking into the seawater, which would not only waste power, but could potentially harm marine life. The insulation is tested rigorously during manufacturing to ensure it has no weak spots or defects. Next comes a layer of steel wires wrapped helically around the insulated conductor. These steel wires, each about as thick as a pencil lead, provide tremendous strength. They allow the cable to be pulled through the water during installation, to hang suspended from the ship's equipment, to be laid across uneven seafloor terrain without breaking. The steel wires are carefully chosen for their strength-to-weight ratio and their resistance to corrosion in seawater. In shallow waters, typically less than 1,000 meters deep, submarine cables are often given additional protection. This armor consists of additional layers of steel wire and sometimes a second outer sheath of polyethylene. The armoring makes the cable thicker and heavier, which is acceptable in shallow water where the cable doesn't have to span long distances without support. Near the shore, where fishing boats or ships' anchors are more likely to interfere with the cable, even heavier armoring may be used, making the cable several inches in diameter. But in the deep ocean, where the seabed lies 2,000 or 3,000 meters down, the cable becomes much thinner. The armor is removed, leaving just the inner layers. This deep-sea cable might be only about 1 inch in diameter, roughly the size of a garden hose, much thinner than you might imagine given that it carries so much of the world's internet traffic. The color of submarine cables is typically black, though this seems arbitrary since no one sees them once they're on the ocean floor. The black outer jacket is made of polyethylene chosen for its resistance to seawater, its flexibility over a wide range of temperatures, and its ability to withstand decades of exposure to the ocean environment. Installing one of these cables is an extraordinary feat of planning and engineering. It begins long before the cable ship leaves port, with months or even years of route surveys. Special survey vessels map the ocean floor along the proposed cable path, using sonar and other instruments to identify any obstacles or hazards. The route must avoid undersea mountains and steep slopes where the cable might slide or become damaged. It must steer clear of active fault zones where earthquakes could snap the cable. It must navigate around known fishing grounds and shipping lanes where possible. Once the route is finalized, the cable is manufactured. This happens in a specialized facility where the various components are assembled and tested. The optical fibers are placed at the center, then the copper conductor, the insulation, the steel wires, all layered together in a process that advances at a steady, measured pace. The finished cable is wound onto giant spools, some as large as a house, ready to be loaded onto the cable ship. The cable ship itself is a remarkable vessel. It has large tanks below decks where the cable spools are stored, allowing the cable to be paid out smoothly during laying operations. It has sophisticated navigation equipment that can position the ship with precision, ensuring the cable follows the planned route. It has specialized machinery on the deck for handling the cable, wheels and pulleys that guide the cable from the storage tanks over the side of the ship and down into the water. The laying process begins near shore, where divers or remotely operated vehicles bury the heavily armored near-shore section of cable in a trench dug into the seabed. This burial protects the cable from anchors and from the strong currents and wave action that occur in shallow water. Once the near-shore cable is secured, the ship begins its slow journey across the ocean. The ship moves at perhaps 3 or 4 knots, carefully following the planned route. As it moves, the cable pays out continuously over the stern, descending through the water column in a graceful curve until it reaches the seafloor, where it settles gently onto the sediment. The rate at which the cable is paid out must be carefully controlled. Too slow, and the cable will be pulled taut between the ship and the seabed, creating tension that could damage it. Too fast, and the cable will form loops or coils on the ocean floor, wasting cable and potentially causing problems later. Along the route, at intervals of 50 to 100 kilometers, the ship stops to install a repeater. The repeater is a pressure-resistant cylinder about the size of a large thermos bottle, packed with electronics. The crew splices the repeater into the cable, connecting the optical fibers and the power conductor. Once the connections are tested and verified, the repeater is lowered over the side and the cable laying resumes. The entire process can take weeks or even months for a long transoceanic cable. The crews work around the clock, monitoring the cable tension, the ship's position, the weather and sea conditions. It's tedious, exacting work that requires constant attention, but when it's done, the result is a data connection that can last for 25 years or more with minimal maintenance. At the other end of the cable, the process reverses. The cable comes ashore at another landing point, where it is buried and eventually terminates in a cable landing station. This station is typically a secure, climate-controlled building located near the coast. Inside are racks of equipment that interface with the cable. Optical line terminal equipment converts the light signals coming from the cable into electrical signals that can be routed to local networks. Power feeding equipment supplies the high-voltage DC power that flows through the cable's copper conductor to energize the repeaters. These cable landing stations are critical nodes in the Internet's infrastructure. They're where the submarine cables connect to terrestrial networks, allowing data to flow from one continent to another. Security at these facilities is tight, as the failure or sabotage of a cable landing station could disrupt Internet connectivity for entire regions. The capacity of modern submarine cables is breathtaking. A single fiber pair in the submarine cable can carry tens of terabits of data per second using dense wavelength division multiplexing. With multiple fiber pairs in a cable, the total capacity can reach hundreds of terabits per second. This is enough bandwidth to support millions of simultaneous video calls, billions of web page loads, countless emails and messages and searches. But cables do sometimes fail. The ocean floor is not a static environment. Undersea earthquakes can trigger landslides that bury or break cables. Fishing trawlers dragging heavy nets across the seabed can snag and damage cables in shallow water. Ships dropping anchors can hook cables and pull them up. Even marine life has been known to damage cables. There are documented cases of sharks biting submarine cables, possibly attracted by the weak electromagnetic fields generated by the power current flowing through the copper conductor. When a cable breaks, the effect can be immediate and dramatic. Internet traffic that was flowing through that cable must be rerouted to other cables, which can become congested. Websites may slow down or become temporarily inaccessible in certain regions. This is why the Internet's infrastructure includes redundancy. Most high-traffic routes, like those across the Atlantic or Pacific Oceans, are served by multiple cables. If one fails, traffic can be diverted to the others. Repairing a submarine cable is a slow, expensive process. First, the exact location of the break must be determined. This is done by sending test signals into the cable from both ends and measuring how far they travel before reflecting back from the break. Once the break is located, a repair ship must travel to that location, which could be hundreds or thousands of miles from shore. The repair ship drags a grapnel, a kind of hook, along the sea floor to snag the cable and pull it up. This can take many hours or even days, especially if the water is deep or the sea conditions are rough. Once one end of the cable is brought to the surface, it is cut, and a new section of cable is spliced onto it. This new section includes extra length to create slack. The first end is then lowered back to the sea floor, and the process is repeated to recover the other end of the break. Finally, the two new ends are spliced together on the ship, and the repaired cable, with its new section creating a gentle loop on the ocean floor, is lowered back down. The entire repair process can take several weeks from the time the break occurs to the time the cable is back in service. During this time, Internet traffic must flow through other routes. This is why cable operators invest in multiple cables along important routes, and why they coordinate their cable paths to avoid single points of failure. The history of submarine cables stretches back far before the Internet, all the way to the mid-1800s, when the first telegraph cables were laid across the English Channel and then the Atlantic Ocean. Those early cables used copper conductors to carry electrical telegraph signals. Dots and dashes form in letters and words. The technology was primitive by today's standards, with low speed and high failure rates, but it represented an enormous leap forward in global communication. Over the decades, the cables evolved. Coaxial cables replaced simple copper conductors, allowing for telephone calls to be carried across oceans. These coaxial cables dominated transoceanic communication through most of the 20th century. But in 1988, the first fiber-optic submarine cable, TAT-8, was laid across the Atlantic. It could carry the equivalent of 40,000 simultaneous phone calls, far more than any coaxial cable. Since then, the shift to fiber optics has been complete. Every new submarine cable uses optical fiber. The old coaxial cables have been retired, their copper conductors too slow and too limited for the demands of modern Internet traffic. Today's submarine cables carry not phone calls but data, the packets of information that make up web pages, videos, emails, everything that flows across the internet. Looking at a map of submarine cables, you can see the patterns of global communication and commerce. Dense networks of cables connect North America and Europe, crossing the Atlantic via multiple parallel routes. Other cables span the Pacific, linking North America with Asia. Still others connect Europe, the Middle East, and Asia, running through the Mediterranean and around Africa or through the Red Sea. South America is connected to North America and to Africa. Australia is linked to Asia and to the Americas. Some of these cables are owned by telecommunications companies. Others are owned by consortiums, groups of companies that share the costs of building and operating the cable. And increasingly, major internet companies like Google, Microsoft, Amazon, and Facebook have become cable owners, building cables to carry their own traffic between their data centers on different continents. These content provider cables represent a significant shift in the economics and control of submarine cable infrastructure. The submarine cable industry is quiet and specialized, with only a handful of companies in the world capable of manufacturing and laying these cables. The expertise required is significant, combining knowledge of fiber optics, high-voltage electrical systems, marine engineering, and oceanography. The ships are expensive to build and maintain, and the cable itself is costly to produce. A single transoceanic cable system can cost several $100 million to build. Yet, for all this cost and complexity, submarine cables remain the most economical way to carry large amounts of data across oceans. Satellites, despite their advanced technology, simply cannot compete with the capacity and cost-effectiveness of fiber optic cables. A satellite link might carry a few gigabits per second at best. A submarine cable carries terabits per second, thousands of times more capacity. And while satellites wear out and must be replaced every 10 to 15 years, a well-maintained submarine cable can operate for 25 years or longer. So as you drift off to sleep, imagine these cables lying on the ocean floor, perfectly still in the cold darkness of the deep sea. No one sees them. No one thinks about them. But they carry the world's conversations, the world's knowledge, the world's connections. They are the invisible threads that bind continents together, that make the internet truly global, that allow someone in Tokyo to watch a video hosted in California, or someone in London to access files stored in Sydney. The internet is not just software and servers. It is also thousands of miles of glass and steel and copper lying quiet on the seabed, patiently carrying light and data from one side of the world to the other. When people think about the internet, they often imagine something ethereal, something existing in the cloud, weightless and boundless. But the truth is that the internet has mass and location. It exists in buildings, large windowless structures scattered across the world, buildings filled with computers and cooling systems and power supplies. These are data centers, and they are where the internet actually lives. A data center is essentially a warehouse for computers. Inside its walls are thousands of servers, each one a computer designed not for human interaction, but for processing and storing data. These servers run continuously, day and night, responding to requests from users all over the world. When you load a web page or stream a video or check your email, you are reaching out to servers in a data center somewhere, perhaps nearby, perhaps thousands of miles away. The physical structure of a data center is built around a single overriding concern: keeping the servers running without interruption. Every aspect of the building's design serves this goal. The location is chosen carefully, away from flood zones and earthquake faults, with good network connectivity and access to reliable electrical power. The building itself is sturdy, often constructed of concrete and steel, able to withstand severe weather. Windows are few or non-existent, not for secrecy, but because windows are weak points that could be breached, and because the servers inside have no need for natural light. Security begins at the perimeter. A data center is typically surrounded by fencing, often topped with barbed wire or razor wire. Security cameras monitor every approach. Guards check credentials at the gate. Only authorized personnel are allowed to enter, and even they must pass through multiple layers of security. Biometric scanners that read fingerprints or iris patterns, keycard readers, man-trap doors that require one door to close before the next will open. The reason for this tight security is simple. The servers inside contain valuable data and provide critical services. Any disruption or unauthorized access could have severe consequences. Inside the building, the layout is organized around efficiency and redundancy. The heart of the data center is the server floor, a large open space, often the size of a warehouse or aircraft hangar. The floor is typically raised, elevated on adjustable pedestals that create a space of perhaps 18 to 36 inches beneath the surface. This space is the plenum, and it serves as a channel for cool air to flow. The servers themselves are mounted in racks, tall metal frames that stand in long rows across the floor. Each rack is about 6 or 7 feet tall, 2 feet wide, and 3 feet deep. The front of the rack has a door that opens to reveal the servers mounted inside, stacked one above another like books on a shelf. The back of the rack may be open or may have another door, and behind the servers, a dense tangle of cables connects them to power and network infrastructure. These racks are arranged in alternating rows facing each other, creating what's called a hot aisle and cold aisle configuration. In a cold aisle, the fronts of 2 rows of racks face each other, creating a corridor between them. In a hot aisle, the backs of 2 rows of racks face each other. The reason for this arrangement has to do with how the servers are cooled. Each server has fans inside it that pull air in through the front and exhaust it out the back. The air entering the front should be cool, which is why the front faces the cold aisle. The air exhausted out the back is hot, heated by the electronic components inside the server, which is why the back faces the hot aisle. By separating the cold supply air from the hot exhaust air, the data center can cool its servers more efficiently. The cooling system in a data center is a major concern because servers generate an enormous amount of heat. A single server might consume 300 to 500 watts of power, and nearly all of that power is converted to heat. With thousands of servers in a data center, the total heat output can be measured in megawatts. If this heat is not removed, the servers will overheat and shut down or be damaged. The traditional approach to cooling is to use computer room air conditioning units, or CRACs, which work much like the air conditioner in a home, but on a much larger scale. Cool air is blown into the plenum beneath the raised floor, and perforated floor tiles in the cold aisles allow this air to rise up in front of the servers. The servers pull the air in, the air flows through them, picking up heat, and the hot air exhausts into the hot aisles. From there, the hot air rises and is drawn back to the crack units, which remove the heat and send the cooled air back into the plenum. It's a continuous cycle, air moving constantly through the data center. More advanced data centers use containment systems to improve efficiency. In hot aisle containment, the hot aisles are enclosed with walls and a ceiling, creating a separate space where the hot exhaust air is isolated from the rest of the room. This hot air is then efficiently returned to the cooling equipment without mixing with the cool air in the cold aisles. Cold aisle containment works similarly but encloses the cold aisles, ensuring that the cool supply air goes directly to the servers without being warmed by the ambient room air. Some data centers are moving beyond air cooling altogether. Liquid cooling, where coolant flows through pipes to remove heat directly from components, is becoming more common, especially for high-density computing, where servers are packed closely together and generate intense heat. In direct-to-chip liquid cooling, cold plates are mounted directly on the processors inside the servers, with liquid flowing through the plates to carry away heat. This liquid, usually water mixed with glycol, is much more efficient at removing heat than air, allowing for higher computing densities and lower energy costs. The most extreme form of liquid cooling is immersion cooling, where entire servers are submerged in a tank of dielectric fluid, a special liquid that does not conduct electricity. The servers operate while fully immersed, and the heat they generate is transferred directly to the surrounding fluid, which circulates through a heat exchanger to dissipate the heat. Immersion cooling is still relatively rare, but it represents the cutting edge of data center cooling technology. Regardless of the cooling method, the goal is the same: to maintain the servers within their optimal temperature range, typically between 64 and 81 degrees Fahrenheit. Too cold, and energy is wasted on unnecessary cooling. Too hot, and the servers risk overheating. Data centers monitor temperature constantly, with sensors throughout the facility feeding data to automated control systems that adjust cooling output in real time. Power is the other critical infrastructure in a data center. The servers, the cooling systems, the networking equipment, all of it requires electricity, vast amounts of it. A large data center might consume 50 or 100 megawatts of power, enough to power tens of thousands of homes. This power typically comes from the electrical grid, delivered through high-voltage lines to substations on the data center property, where it is stepped down to the voltages needed for the equipment inside. But the grid is not perfectly reliable. Power outages can occur due to storms, equipment failures, or accidents. For a data center, even a brief power interruption is unacceptable. If the servers lose power, they shut down abruptly, potentially losing data and disrupting services for millions of users. To prevent this, data centers include backup power systems with multiple layers of redundancy. The first layer is uninterruptible power supplies, or UPS units. A UPS is essentially a large battery bank that can provide power for a short time, typically 10 to 20 minutes. If the grid power fails, the UPS activates instantly, so quickly that the servers never notice the interruption. During those 10 to 20 minutes, the UPS buys time for the second layer of backup power to start. This second layer consists of diesel generators, large engines that can generate megawatts of power by burning diesel fuel. When grid power fails, the generators start automatically, reaching full power output within a minute or two. The UPS bridges the gap, providing power until the generators are online. Once the generators are running, they can continue for days as long as fuel is available. Data centers typically have fuel storage tanks capable of supplying the generators for 24 to 48 hours, and they have contracts with fuel suppliers to deliver additional fuel if an outage is prolonged. The power distribution within the data center is designed with equal attention to reliability. Power flows from the UPS and generators through redundant distribution paths, often called A and B power. Each server has two power supplies, one connected to the A path and one to the B path. If one power supply or one distribution path fails, the server continues operating on the other. This N+N redundancy, where every critical component has a duplicate, ensures that no single failure can bring down the data center. The servers themselves are the heart of the operation. In a typical server, you would find components similar to a desktop computer: a motherboard with one or more processors, memory modules, storage drives, and network interface cards. But servers are optimized differently than desktop computers. They are designed for reliability and density, not for graphics or multimedia. They typically have no monitors, keyboards, or mice. All interaction with the servers happens remotely over the network. The processors in servers are often similar to those in desktop computers, but may be chosen for different characteristics. Where a desktop CPU might prioritize single-threaded performance for responsiveness, a server CPU might prioritize core count and efficiency, allowing it to handle many tasks simultaneously. These CPUs have features specifically for servers, like error-correcting code memory support, which can detect and correct data corruption, and virtualization extensions, which allow multiple virtual machines to run efficiently on the same hardware. Memory in servers is typically ECC, or error-correcting code memory, which adds redundancy to detect and correct bit errors that can occur due to cosmic rays or electronic noise. With gigabytes or terabytes of memory in a server, the probability of an error occurring increases, and ECC memory helps ensure data integrity. Storage in servers might be spinning hard disk drives or solid-state drives, depending on the application. Hard drives are cheaper per gigabyte and are used where large amounts of data need to be stored inexpensively. Solid-state drives are faster and more reliable, with no moving parts, and are used where speed is critical. Many servers use a combination, with SSDs for the operating system and active data, and HDDs for bulk storage. Networking is crucial in a data center. Servers are connected to switches, network devices that create a local network within the data center. These switches are typically high-speed, using 10 gigabit or 25 gigabit or even 100 gigabit Ethernet connections. The switches are arranged in a hierarchical topology, with access switches connecting directly to the servers, aggregation switches connecting the access switches together, and core switches connecting the aggregation switches and providing connections to the wider internet. The cabling in a data center is extensive. Each server has at least 2 network cables, often more, connecting it to the switches. These cables, along with power cables and other connections, create a dense web of infrastructure. Cable management is important, not just for neatness, but for airflow. Poorly managed cables can block air paths, creating hotspots where cooling is inadequate. Data centers also have out-of-band management networks, separate from the main data network. This management network allows administrators to access servers even if the main network is down or if a server's operating system has crashed. Each server has a baseboard management controller, a small computer built into the server's motherboard that has its own network connection and can power the server on or off, monitor its health, and provide remote console access. The software that runs on these servers is diverse. Some servers run web servers, software that delivers web pages to users' browsers. Others run database servers, managing the storage and retrieval of structured data. Still others run application servers, hosting the complex business logic of web applications. Many servers run virtualization software, allowing multiple virtual machines to run on the same physical hardware, increasing efficiency and flexibility. Beyond the servers themselves, a data center includes many support systems. HVAC equipment, electrical switchgear, fire suppression systems, monitoring equipment, and security systems all work together to keep the facility operating. Fire suppression is particularly important because water sprinklers, the traditional method of fire suppression, could damage electronic equipment. Instead, data centers often use gaseous fire suppression systems that flood the room with an inert gas that displaces oxygen, smothering fires without harming equipment. Monitoring systems track thousands of data points: temperature, humidity, power consumption, network traffic, server health. This data feeds into centralized monitoring consoles where operators can see the status of the entire facility at a glance. Alerts are generated automatically if any parameter goes out of range, allowing issues to be addressed before they become problems. The location of data centers around the world reflects both the distribution of Internet users and the practicalities of power and connectivity. Major hubs exist in Northern Virginia near Washington, D.C., where plentiful fiber optic connectivity and political stability make it an attractive location. Silicon Valley hosts many data centers serving the tech industry. Singapore, Tokyo, London, Frankfurt, and Sydney are hubs for their respective regions. And increasingly, data centers are being built in cooler climates, where less energy is needed for cooling, or near sources of renewable energy, where power can be obtained sustainably. The environmental impact of data centers is significant. The electricity they consume produces carbon emissions, and the water used in cooling systems can strain local resources. In response, the industry has been working to improve efficiency. Metrics like power usage effectiveness, or PU, measure how much of a data center's total power consumption goes to the servers versus how much goes to cooling and other overhead. The best data centers have PUEs approaching 1.1, meaning only 10% of their power goes to overhead, with 90% powering the servers themselves. Some data centers use free cooling, taking advantage of outside air when it's cold enough to cool the facility without mechanical refrigeration. In colder climates, this can be effective for much of the year. Other data centers use waste heat productively, capturing the hot air from the servers and using it to heat nearby buildings or greenhouses. These innovations help reduce the environmental footprint of our digital infrastructure. As you relax, imagine the rows of racks, the cool air flowing, the blinking lights on thousands of servers, all working silently, processing data, serving requests, storing information. Imagine the hum of cooling fans, the soft whoosh of air through the raised floor, the occasional click of a hard drive. This is where the internet lives, in these carefully controlled environments, in these warehouses of computation. When you tap a screen or type a search, your request travels to one of these places, to a server in one of these racks, and then the response travels back to you. All of it happening in the blink of an eye, all of it made possible by this quiet, industrious infrastructure. If data centers are where the internet lives, and cables are how it's connected, then routers and switches are the traffic directors, the devices that determine where every packet of data goes. They are the decision makers, the pathfinders, quietly and efficiently moving information from source to destination across networks large and small. Understanding routers and switches means understanding something fundamental about how networks are organized. A network is not just a collection of computers connected together. It's a structured, hierarchical system where different devices play different roles. Some devices, like the server in the data center or the laptop on your desk, generate and consume data. They are the endpoints, the source and destination of information. But between these endpoints are intermediary devices that simply move data along, and these are the routers and switches. Let's begin with switches, because they operate at a more local level, connecting devices within a single network. A switch is a device with multiple ports, physical sockets into which you plug network cables. When you connect a computer to a switch, you're connecting it to a local area network, a LAN. That includes all the other devices connected to that switch and potentially other switches as well. The fundamental job of a switch is simple. When it receives a frame, a packet of data from one port, it determines which port should receive that frame and forwards it there. To do this, the switch maintains a table, sometimes called a MAC address table or CAM table, that maps each device's unique MAC address, a hardware identifier burned into its network interface card, to the port where that device is connected. When a frame arrives at a port, the switch examines the destination MAC address in the frame's header. It looks up that address in its table. If it finds a match, it forwards the frame only to the port where that device is connected. If it doesn't find a match because the destination device is unknown, the switch floods the frame, sending it out all ports except the one it came in on. Eventually, the destination device will respond, and the switch will learn which port that device is connected to, adding that information to its table. This learning process happens automatically and continuously. Every time a device sends a frame, the switch notes the source MAC address and the port it came from, updating its table. Over time, the switch builds a complete map of which devices are connected to which ports. This map allows the switch to forward frames efficiently, sending each frame only where it needs to go, reducing unnecessary traffic on the network. There are different types of switches. Unmanaged switches are simple devices that just do the basic job of forwarding frames. They require no configuration and have no way to be managed remotely. You plug them in, connect your devices, and they work. They're inexpensive and suitable for small networks where simplicity is more important than advanced features. Managed switches, on the other hand, offer much more control. They can be configured remotely through a web interface or command line interface. They support features like VLANs, virtual local area networks, which allow a single physical switch to be divided into multiple logical networks, isolating traffic between them. They support quality of service, prioritizing certain types of traffic over others to ensure that time-sensitive applications like voice calls or video streams get the bandwidth they need. They support port mirroring, copying traffic from one port to another for monitoring or troubleshooting. And they support various security features, like port security, that restricts which devices can connect to which ports. In large networks, switches are arranged in hierarchies. At the bottom are access switches, the switches that end-user devices connect to directly. Each access switch might have 24 or 48 ports. Above the access switches are distribution or aggregation switches, which connect multiple access switches together. At the top are core switches, high-capacity devices that connect the distribution switches and provide connections to routers and the wider Internet. This hierarchical design has several advantages. It reduces the load on any single switch, spreading the traffic across multiple devices. It provides redundancy, so if one switch fails, traffic can be rerouted through others. And it allows for easy expansion, with new access switches being added as needed without disrupting the core of the network. Routers, unlike switches, operate at a different level of abstraction. While a switch forwards frames within a local network using MAC addresses, a router forwards packets between networks using IP addresses. An IP address is a logical address assigned to a device by software that identifies both the network the device is on and the device's position within that network. A router has multiple network interfaces, each connected to a different network. When a packet arrives at one of these interfaces, the router examines the destination IP address in the packet's header. It consults its routing table, a database that maps IP address ranges to network interfaces. Based on this table, the router determines which interface should receive the packet and forwards it there. The packet then continues its journey, possibly passing through more routers, until it reaches its destination network. The routing table can be configured manually by a network administrator who specifies static routes indicating which networks can be reached through which interfaces. Or the routing table can be built automatically using routing protocols, which are algorithms that allow routers to communicate with each other and exchange information about network topology. These protocols enable routers to discover available paths through the network and to adapt if paths become unavailable due to failures or congestion. Common routing protocols include RIP, the Routing Information Protocol, which is simple but limited. OSPF, Open Shortest Path First, which is more sophisticated and scales better to larger networks. And BGP, the Border Gateway Protocol, which is used to route traffic between different autonomous systems on the Internet, between different organizations' networks. BGP is particularly important because it's the protocol that makes the global Internet work. Every organization that connects to the Internet, whether it's an ISP, a university, a corporation, or a data center, is assigned a block of IP addresses and an autonomous system number. BGP allows these organizations to announce their IP address blocks to their neighbors, saying essentially, "If you have traffic destined for these addresses, send it to me." These announcements propagate across the Internet, allowing every router to learn a path to every IP address. The home router you might have in your house or apartment is a simplified consumer-grade version of the routers used in enterprise networks and on the Internet backbone. It combines several functions in one device. It's a router connecting your local network to your ISP's network. It's also a switch with several ports on the back for connecting devices with Ethernet cables. It's a wireless access point, broadcasting a Wi-Fi signal for wireless devices. And it's often a firewall, filtering traffic to protect your local network from threats. When you connect to the Internet through a home router, your ISP assigns your router a public IP address, an address that identifies your household on the wider Internet. But the devices on your local network, your computers, phones, and tablets, don't use that public address directly. Instead, they use private IP addresses in ranges reserved for local networks. The router performs network address translation, or NNATT, converting between the private addresses used inside your home and the public address used on the Internet. NAT works like this. When a device on your local network sends a packet to the Internet, the router replaces the device's private source IP address with the router's public IP address. The router keeps track of this in a translation table, noting which local device initiated the connection and which port numbers it's using. When a response packet comes back from the Internet, the router looks it up in the translation table, sees which local device it's meant for, replaces the destination address with the device's private address, and forwards it to that device. This NAT function allows many devices to share a single public IP address, which is important because public IP addresses are a limited resource. It also provides a degree of security, hiding the internal structure of your local network from the Internet. Switches and routers both deal with data at the packet level, but they operate at different layers of abstraction, a concept formalized in the OSI model, a framework for understanding network protocols. The OSI model has 7 layers, from physical layer at the bottom, dealing with electrical signals and cables, to application layer at the top, dealing with user-facing protocols like HTTP for web browsing or SMTP for email. Switches typically operate at layer 2, the data link layer, where they work with frames identified by MAC addresses. Routers operate at layer 3, the network layer, where they work with packets identified by IP addresses. But the lines can blur. Layer 3 switches, which combine the functionality of a switch and a router, can forward traffic between different IP subnets while still providing the high port density of a switch. These devices are common in enterprise networks where performance and flexibility are both important. The forwarding process in both switches and routers is designed to be as fast as possible. In a high-end switch or router, packets are processed by dedicated hardware called ASICs, application-specific integrated circuits, which are optimized for the task of examining packet headers and making forwarding decisions. These ASICs can process packets at line rate, meaning they can handle packets arriving at the maximum speed the network interface can receive them, with no slowdown or delay. For particularly critical or high-traffic paths, techniques like link aggregation can combine multiple physical connections into a single logical connection, multiplying the available bandwidth. Redundant paths can be configured so that if one link fails, traffic automatically switches to an alternate path. These features, combined with the inherent redundancy of having multiple routers and switches in a network, help ensure that data keeps flowing even if individual components fail. As you settle into rest, picture the router on your desk or tucked away in a closet, its lights blinking as packets flow through. Picture the switches in the wiring closet of an office building or in the network room of a school, silently forwarding frames between computers and printers and servers. Picture the routers in an ISP's network, in a data center, at the junctions where different networks meet, making decisions about where each packet should go next. Millions of decisions per second, each one a small act of pathfinding, each one bringing data a step closer to its destination. This network of decision-makers, this web of routers and switches, is what allows the Internet to function, to deliver your requests and responses, to connect you to the world. Beneath all the hardware, the cables and routers and switches, lies a set of rules, a language that all devices on the Internet speak. This language is called TCP/IP, short for Transmission Control Protocol, and Internet Protocol. It is the fundamental communication standard that makes the Internet possible, the common ground that allows a laptop in London to talk to a server in Los Angeles, that allows devices from different manufacturers running different operating systems to exchange data seamlessly. TCP/IP is not a single protocol, but a suite of protocols, a collection of standards that work together at different levels. To understand it, we use a model, a conceptual framework that divides the work of networking into layers, each layer providing specific services to the layer above it. The TCP/IP model has 4 layers, each with its own role. At the bottom is the link layer, also called the network access layer. This layer deals with the physical transmission of data over the particular type of network, whether that's Ethernet, Wi-Fi, fiber optic, or any other medium. The link layer handles the details of how bits are turned into electrical signals, or radio waves, or pulses of light, how devices are addressed at the hardware level, how the medium is shared between multiple devices. The link layer is where MAC addresses live, those unique hardware identifiers burned into network interface cards. When a computer wants to send data over an Ethernet network, the link layer adds an Ethernet header to the data, a header that includes the source and destination MAC addresses, the type of data being carried, and other information needed for the Ethernet protocol. The frame, which is what we call a packet at this layer, is then transmitted onto the network, where switches use the MAC addresses to forward it toward its destination. Above the link layer is the Internet layer, the layer where the Internet protocol, IP, operates. IP is responsible for addressing and routing. Every device on the Internet has an IP address, a numerical address, that identifies it. The most common version of IP currently in use is IPv4, which uses 32-bit addresses written as 4 numbers separated by dots, like 192.168.1.1. A 32-bit address allows for about 4.3 billion unique addresses, which sounds like a lot, but has proven insufficient as the Internet has grown. The newer IPv6 uses 128-bit addresses, providing a vastly larger address space. When the Internet layer receives data from the layer above, it adds an IP header to that data, creating an IP packet. This header includes the source IP address, the address of the computer sending the data, and the destination IP address, the address of the computer that should receive the data. The header also includes a time to live field, a counter that decrements each time the packet passes through a router. If the TTL reaches 0, the packet is discarded, preventing packets from circulating endlessly if there's a routing loop. The Internet layer is where routing happens. When a router receives an IP packet, it examines the destination IP address and consults its routing table to decide where to send the packet next. The packet might pass through many routers on its journey from source to destination, each one making its own routing decision based on its own routing table. This process, called packet switching, allows data to flow through the Internet even if some paths are broken or congested, with routers dynamically choosing the best available path. Above the Internet layer is the transport layer, where the Transmission Control Protocol, TCP, and the User Datagram Protocol, UDP, operate. These protocols handle end-to-end communication between applications running on different computers. UDP is the simpler of the two. It provides a way for applications to send individual chunks of data, called datagrams, with minimal overhead. A UDP header is small, containing just the source and destination port numbers, which identify the applications that are communicating, and a lengthen checksum. UDP does not guarantee that datagrams will arrive, that they will arrive in order, or that they will arrive without errors. It just sends them and hopes for the best. This simplicity makes UDP fast and efficient, suitable for applications like video streaming or online gaming, where speed is more important than perfect reliability. TCP, on the other hand, is designed to provide reliable ordered delivery. When an application wants to send data using TCP, it establishes a connection with the destination application. This connection setup is a three-step process called the three-way handshake. The sender sends a SYN packet, short for synchronize, to the receiver. The receiver responds with a SYN-ACK packet, acknowledging the SYN and sending its own synchronization. The sender then sends an ACK packet, acknowledging the receiver's SYN. At this point, a connection is established, and data can flow. TCP breaks data into segments, each one small enough to fit into a single IP packet. Each segment is numbered, allowing the receiver to reassemble them in the correct order, even if they arrive out of sequence. When a segment arrives, the receiver sends an acknowledgement back to the sender, confirming that it received the segment. If the sender doesn't receive an acknowledgement within a certain time, it assumes the segment was lost and retransmits it. This mechanism ensures that all data is eventually delivered, even if some packets are lost in transit. TCP also includes flow control, which prevents a fast sender from overwhelming a slow receiver. The receiver includes information in each acknowledgement about how much data it can receive, and the sender limits its sending rate accordingly. TCP also includes congestion control, mechanisms that detect network congestion and slow down sending to avoid making it worse. These features make TCP suitable for applications like web browsing, email, and file transfers, where reliability and completeness are essential. At the top of the stack is the application layer, where protocols used by user-facing applications reside. HTTP, the Hypertext Transfer Protocol, is used for web browsing. When you type a URL into a browser, the browser uses HTTP to request the web page from a server, and the server uses HTTP to send the page back. HTTPS is a secure version of HTTP that encrypts the communication to prevent eavesdropping. SMTP, the Simple Mail Transfer Protocol, is used for sending email. When you click Send on an email, your email client uses SMTP to deliver the message to your email provider's server. FTP, the File Transfer Protocol, is used for transferring files between computers. DNS, the Domain Name System, translates human-readable domain names like example.com into IP addresses that computers can use. These and many other application layer protocols define how specific applications communicate over the network. The beauty of this layered model is that each layer can be changed independently without affecting the others. You can use TCP over Ethernet, over Wi-Fi, over fiber optic, over any link layer technology, and it works the same. You can run HTTP over TCP, over IPv4, or over IPv6, or over any other network layer protocol, and the application doesn't need to change. This flexibility is a key reason the Internet has been so successful and so adaptable. Let's trace the journey of a packet as it moves through these layers. Suppose you're loading a web page. Your browser, running at the application layer, uses HTTP to send a GET request to the web server, asking for the page. This request is handed down to the transport layer, where TCP breaks it into segments, adds TCP headers with sequence numbers and port numbers, and hands them to the Internet layer. The Internet layer adds IP headers with the source and destination IP addresses. Now the data is an IP packet, ready to be transmitted over the network. The packet is handed to the link layer, which adds an Ethernet header or a Wi-Fi header, depending on how your computer is connected to the network. The frame is then transmitted, traveling as electrical signals over Ethernet cables or as radio waves through the air. When the frame reaches your router, the link layer strips off the Ethernet or Wi-Fi header and passes the IP packet to the Internet layer. The router examines the destination IP address, consults its routing table, and determines that the packet should be forwarded to your ISP. It adds a new link layer header appropriate for the connection to the ISP and sends the frame on its way. The packet might pass through multiple routers, each one stripping off the link layer header, examining the IP header, consulting its routing table, and adding a new link layer header before forwarding the packet. This process, called decapsulation and encapsulation, happens at each hop along the path. The IP header remains constant, carrying the source and destination addresses, but the link layer header changes at each hop as the packet moves from one network to another. Eventually, the packet reaches the data center where the web server resides. The server's network interface receives the frame, strips off the link layer header, and passes the IP packet to the operating system. The operating system strips off the IP header, examines the destination port number in the TCP header, and determines that the segment is meant for the web server application. The web server receives the segment, sends an acknowledgement back to your browser, and processes the request. The web server constructs a response, the HTML of the web page, and sends it back. The process reverses, with the data moving down through the layers on the server, across the internet through multiple routers, and back up through the layers on your computer. Your browser receives the HTML, parses it, renders the page, and displays it on your screen. All of this happens in a fraction of a second, so fast that it seems instantaneous. One of the remarkable features of TCP/IP is its resilience. Because routers make independent forwarding decisions, and because TCP can retransmit lost segments, the network can adapt to failures and congestion without requiring any centralized control. If a router fails, other routers detect that it's unreachable and route packets around it. If a link becomes congested, TCP's congestion control mechanisms cause senders to slow down, reducing the load. This decentralized, adaptive design is what allows the Internet to scale to billions of devices and to continue functioning even in the face of equipment failures, cable cuts, and other disruptions. As you drift off, imagine these layers, each one abstracting away the complexity of the layers below, each one providing a service to the layers above. Imagine packets moving through the network, headers being added and removed, routers making forwarding decisions, segments being acknowledged and retransmitted. It's a symphony of protocols working together, a carefully orchestrated system that makes the chaos of billions of devices communicating seem orderly and manageable. The Internet is not magic. It's engineering, layer upon layer of protocol and agreement, allowing devices that have never met to speak a common language to exchange information, to connect. When you type a web address into your browser, you're using words, human-readable names like example.com or google.com or wikipedia.org. But computers don't communicate using words. They communicate using numbers. IP addresses like 192.0.2.1 or 2001, 0DB8, 85, A3, 0000, 0000, 8A2E, 0370, 7334. Somewhere between your typing and the computer connecting, a translation must happen, converting the name you typed into the numerical address the computer needs. This translation is performed by the Domain Name System. DNS, one of the most critical and yet least visible parts of the Internet's infrastructure. DNS is often compared to a phone book, a directory that maps names to numbers. But unlike a phone book, which is a static printed directory, DNS is a distributed, hierarchical, dynamic system involving thousands of servers worldwide, constantly updating and responding to billions of queries every day. Let's understand how it works by following what happens when you type a domain name into your browser. Suppose you type example.com. Your browser needs to find the IP address associated with that name, so it initiates a DNS query. The first place the query goes is to your computer's local DNS cache. Your operating system maintains a cache of recent DNS lookups, storing the results temporarily so that if you visit the same site again soon, it doesn't have to repeat the lookup. If example.com is in the cache and the cached result hasn't expired, the query ends here. Your computer uses the cached IP address and starts connecting to the server. But if it's not in the cache, the query continues. Your computer sends the DNS query to a DNS resolver, typically a server operated by your internet service provider. This resolver is configured automatically when you connect to your ISP's network. The resolver acts as an intermediary, performing the complex task of looking up domain names so that your computer doesn't have to. The resolver also has a cache, a much larger and longer-lasting cache than your computer's. If it has recently looked up example.com for another customer, it will use the cached result and send it back to your computer immediately. But if it's not in the resolver's cache, the lookup process begins in earnest. The DNS system is organized hierarchically, like an upside-down tree. At the top, the root, are 13 sets of root servers. These are not 13 physical servers, but 13 IP addresses, each one representing multiple servers distributed around the world using a technique called anycast, where many servers share the same IP address and a router's direct queries to the nearest one. The root servers don't know the IP addresses of every domain on the Internet. Instead, they know where to find the servers that do. The resolver starts by sending a query to one of the root servers, asking for example.com. The root server doesn't know the IP address of example.com, but it knows which servers are responsible for the .com top-level domain. It responds with a referral, sending back a list of the .com TLD servers. The resolver then queries one of these .com TLD servers, asking again for example.com. The TLD server doesn't know the IP address either, but it knows which name servers are authoritative, for example.com. It responds with another referral, providing the addresses of example.com, quote, authoritative name servers. These authoritative name servers are the final authority on example.com. They are typically operated by the organization that owns the domain or by a DNS hosting provider on their behalf. The resolver queries one of these authoritative servers, and this server responds with the answer. The IP address of example.com is 192.0.2.1. The resolver caches this result so that future queries for example.com can be answered immediately and sends the IP address back to your computer. Your computer also caches the result and passes it to the browser. Finally, the browser can establish a connection to 192.0.2.1 and start loading the web page. This entire process, from your typing the URL to your computer receiving the IP address, typically takes less than 100 milliseconds. It happens so quickly that you barely notice the delay. But in that brief moment, multiple servers were consulted, queries were sent and responses received, caches were checked and updated. It's a complex dance performed billions of times per day across the Internet. The records stored in DNS are more than just domain names and IP addresses. DNS supports many types of records, each serving a different purpose. The most common is the A record, which maps a domain name to an IPv4 address. Ballet records map names to IPv6 addresses. MX records specify the mail servers responsible for receiving email for a domain. CNAME records create aliases, allowing one domain name to point to another. TXT records store arbitrary text, often used for domain verification or security purposes. Each DNS record also has a time to live, or TTL, a value that specifies how long the record should be cached before it's considered stale and must be looked up again. Shorter TTLs allow for rapid changes, such as when a service is being migrated from one server to another, but they increase the load on DNS servers because resolvers have to query more frequently. Longer TTLs reduce the load, but make changes slower to propagate. Typical TTLs range from a few minutes to 24 hours. The zone file is the database where these records are stored. A zone file contains all the DNS records for a particular domain or subdomain. It's typically a text file with a specific format, though many DNS hosting providers offer web interfaces for editing zones without having to work with the raw file format. When you register a domain, you specify which name servers are authoritative for your domain, and those name servers host your zone file. DNS security is an important concern. Because DNS queries and responses travel unencrypted over the network, they can be intercepted and modified. An attacker could return a false IP address in response to a DNS query, directing users to a malicious server. This is called DNS spoofing or DNS poisoning. To combat this, DNS security extensions, DNSSEC, were developed. DNSSEC uses cryptographic signatures to verify that DNS responses come from the authoritative source and haven't been tampered with. With DNSSEC, each DNS record is signed with a private key, and the corresponding public key is published in DNS. When a resolver receives a signed response, it can verify the signature using the public key, ensuring the response is authentic. DNSSEC requires a chain of trust, with each level of the DNS hierarchy signing the keys of the level below, all the way up to the root zone, whose key is trusted by default. Another security enhancement is DNS over HTTPS, or DOH, and DNS over TLS, or DOT. These protocols encrypt DNS queries and responses, preventing eavesdropping and manipulation. Instead of sending queries to the ISP's resolver over unencrypted UDP or TCP, the client sends them over an encrypted HTTPS or TLS connection to a DOH or DOT server. This provides privacy, ensuring that ISPs and other intermediaries cannot see which domain names you're looking up. Reverse DNS works in the opposite direction, translating IP addresses back to domain names. This is done using a special domain called in-ada.arpa for IPv4 or IP6.arpa for IPv6. The IP address is reversed and appended to this domain to create a query. For example, to do a reverse lookup of 192.0.2.1, the query would be for 1.2. 0.192.in-ada.arpa. Reverse DNS is often used for logging and security purposes, allowing administrators to see the host names associated with IP addresses in their logs. DNS load balancing is another important application. A domain name can have multiple A records, each pointing to a different IP address. When a resolver queries for that domain, the authoritative server can return all the IP addresses in a round-robin fashion, distributing requests across multiple servers. More sophisticated systems use geographic DNS, returning different IP addresses based on where the query originated, directing users to the server closest to them for lower latency. Content delivery networks, CDNs, make heavy use of DNS for directing traffic. When you request a file from a CDN, such as an image or video, the domain name resolves to an IP address of a CDN server near you. The CDN's DNS system uses complex logic to determine the best server based on the requester's location, the current load on various servers, and the availability of the content. This ensures that users receive content quickly from a nearby server, rather than having to retrieve it from a distant origin server. DNS is also used for discovering services. SRV records allow a domain to specify which servers provide a particular service and on which ports. For example, an SRV record might specify that IMAP email service. For example, .com is provided by mail.example.com on port 993. Applications can query for these SRV records to automatically discover service endpoints without requiring hard-coded configuration. The resilience of DNS is critical. If DNS fails, the Internet effectively stops working, because without name resolution, users cannot connect to servers by domain name. For this reason, DNS infrastructure is heavily redundant. Each domain typically has multiple authoritative name servers, often hosted in different locations or by different providers. Resolvers are configured with multiple root servers and multiple TLD servers to query. And the caching at every level means that even if some DNS servers become unreachable, cached results continue to work for a time. DNS attacks can disrupt services. Distributed denial of service attacks, DDoS attacks, can flood DNS servers with massive numbers of queries, overwhelming them and preventing legitimate queries from being answered. These attacks are particularly effective against DNS because DNS queries are small and easy to generate, while the lookup process can be resource-intensive for the server. Mitigation involves large-scale infrastructure capable of absorbing the attack traffic and filtering out malicious queries. As you close your eyes, think of DNS as the gentle guide that makes the Internet navigable. Without it, we would be lost in a sea of numbers, forced to memorize IP addresses or keep our own directories. With it, we can type simple names, and the system finds the numbers for us, quietly and efficiently. It's a service we take for granted, a system so reliable that we only notice it when it fails. But every moment, millions of queries are being answered, names are being translated to addresses, connections are being made possible. The domain name system is the invisible librarian of the Internet, always ready with an answer, always pointing us in the right direction. The Internet is not a single entity owned by one organization. It is a network of networks, thousands of independent networks, all interconnected through agreements and infrastructure. At the center of this interconnection are Internet service providers, ISPs, the companies that provide Internet access to homes, businesses, and organizations. Without ISPs, most of us would have no way to connect to the Internet. They are the gatekeepers, the entry points through which our data flows into and out of the global network. ISPs exist at different scales and serve different roles. To understand how they work, we use a tier system, a hierarchical classification that describes how ISPs connect to each other and to the Internet backbone. At the top are Tier 1 ISPs, the largest and most globally connected networks. Tier 1 ISPs have networks that span continents, with connections in multiple countries and often ownership of long-haul fiber optic cables, including submarine cables. What defines a Tier 1 ISP is that they can reach the entire Internet without having to pay anyone else for transit. They achieve this through peering relationships, agreements to exchange traffic with other Tier 1 networks at no cost. Peering works like this. Two networks agree to connect their infrastructure, typically at an Internet exchange point, and to exchange traffic destined for each other's networks. Neither network charges the other. This is called settlement-free peering, and it's only possible when both networks bring roughly equal value to the relationship. Tier 1 ISPs peer with each other because each one has a large network with many customers, and neither wants to pay the other for transit. Together, the Tier 1 ISPs form the Internet backbone, the core infrastructure that all other networks rely on. There is only a handful of true Tier 1 ISPs in the world. Their names might be familiar: Atant, Verizon, Lumen Technologies, NTT, Deutsche Telekom, and a few others. These networks operate massive infrastructure with high-capacity routers and switches in cities around the world, connected by fiber optic links that can carry terabits of data per second. Below the Tier 1 networks are Tier 2 ISPs. These are regional or national networks that don't span the entire globe, but have significant infrastructure within their coverage area. Tier 2 ISPs peer with some networks but also purchase transit from Tier 1 ISPs. Transit is the service of carrying traffic to destinations the Tier 2 ISP can't reach directly through its own network or peering agreements. The Tier 2 ISP pays the Tier 1 ISP for this service, typically based on the volume of traffic or the capacity of the connection. Tier 2 ISPs serve businesses, other smaller ISPs, and sometimes large residential customers. They have their own backbone networks within their region, with routers in major cities and fiber connections between them. They may own or lease fiber optic cables, connecting their network to their customers and to other networks. At the bottom of the hierarchy are Tier 3 ISPs. These are local or regional providers that primarily serve residential customers and small businesses. Tier 3 ISPs don't peer with other networks. Instead, they purchase transit from one or more Tier 2 or Tier 1 ISPs. This transit provides the Tier 3 ISP with access to the entire Internet. The Tier 3 ISP then resells this access to its customers, providing them with Internet service through various technologies like DSL, cable, fiber, or wireless. The transition from your home to the Internet follows a path through this hierarchy. Your home router connects to your ISP, likely a Tier 3 ISP. This connection might use a cable modem, which transmits data over the same coaxial cable that delivers television. Or it might use DSL, digital subscriber line, which transmits data over traditional telephone lines using frequencies above those used for voice calls. Or if you're lucky, it might use fiber optic cable, providing a direct fiber connection from your home to the ISP's network. Regardless of the technology, the data from your home travels to a piece of equipment in your neighborhood. For cable, this is typically a node, a box mounted on a utility pole or in a pedestal, where the coaxial cables from many homes are aggregated. For DSL, it's a DSLAM, a digital subscriber line access multiplexer, typically located in a telephone company building or outdoor cabinet. For fiber, it's an optical line terminal, or OLT, which might be located at a central office or a neighborhood cabinet. From these aggregation points, data travels over fiber optic links to the ISP's core network, where it passes through routers and switches. The ISP's network is structured much like any large network, with edge routers at the periphery connecting to customers and core routers in the center connecting to other networks. If your data is destined for another customer of the same ISP, it might stay within that ISP's network, flowing from your edge router through the core to another edge router and then to the destination customer. But if your data is destined for someone on a different network, it must leave your ISP's network and travel through the Internet. At this point, it reaches the ISP's upstream connections, the links where the Tier 3 ISP connects to its Tier 2 or Tier 1 transit provider. The traffic flows over these links, paid for by your ISP as part of its transit agreement, and enters the transit provider's network. From there, the data might pass through several more ISPs. If your ISP's transit provider can reach the destination directly, the data flows through that network. If not, the transit provider might hand the data off to one of its peers or to its own upstream provider, following the path of BGP routes until it reaches the destination network. At each handoff point, routers examine the destination IP address, consult their routing tables, and forward the packet to the next hop. Eventually, the data reaches the destination network, flows through its core and edge routers, and arrives at the destination device. The response follows a similar path in reverse, traveling back through the networks until it reaches your home. All of this happens in milliseconds, the journey from source to destination traversing multiple networks and multiple ISPs so quickly that you perceive it as instantaneous. The business model of ISPs is based on selling bandwidth, the capacity to transmit data. Residential customers typically purchase a service tier with a specific download and upload speed, such as 100 megabits per second download and 20 megabits per second upload. The ISP provisions enough capacity in its network to provide these speeds to all its customers, though not necessarily simultaneously. ISPs oversubscribe, selling more total bandwidth to customers than they have in their upstream connections, based on the assumption that not all customers will use their maximum bandwidth at the same time. This oversubscription works most of the time, but during peak usage periods, typically evenings when many people are streaming video, the ISP's network can become congested. When this happens, speeds slow down, buffering increases, and the user experience degrades. ISPs manage this by increasing capacity when congestion becomes chronic, either by upgrading equipment or purchasing more upstream transit. Business customers often purchase dedicated connections, sometimes called leased lines or dedicated internet access. These connections provide a guaranteed level of bandwidth and often come with service-level agreements, SLAs, that promise a certain level of uptime and performance. The cost is much higher than residential service, but the reliability and consistency are essential for businesses that depend on internet connectivity. ISPs also provide additional services beyond simple internet access. They might host email servers, providing email accounts for their customers. They might offer web hosting, allowing customers to host websites on the ISP's servers. They might provide DNS services, operating DNS resolvers for their customers to use, and they often provide customer support, helping users troubleshoot connection issues and configure equipment. The infrastructure an ISP operates is substantial. For a cable ISP, this includes the cable plant, the network of coaxial cables running through neighborhoods, the nodes and amplifiers that boost signals, and the head-end equipment where television signals are received and internet data is transmitted onto the cable. For a DSL ISP, it includes the telephone lines, the DSLAMs, and the central offices. For a fiber ISP, it includes the fiber optic cables, the OLTs, and the splitters that divide fiber signals to multiple homes. All of this infrastructure must be maintained. Cables degrade over time and must be repaired or replaced. Equipment fails and must be serviced. Trees fall on lines, animals chew through cables, and technology evolves, requiring upgrades to keep pace with customer demand for faster speeds. The ongoing maintenance and improvement of this infrastructure represents a significant investment for ISPs. Competition among ISPs varies greatly by location. In some areas, multiple ISPs offer service, providing customers with choices and keeping prices competitive. In other areas, only one or two ISPs are available, effectively creating a monopoly or duopoly. This lack of competition can lead to higher prices and poorer service. Regulatory agencies in many countries have sought to encourage competition through measures like requiring incumbent ISPs to share their infrastructure with competitors, allowing new entrants to offer service without having to build their own networks from scratch. Net neutrality is a contentious issue related to ISPs. The principle of net neutrality is that ISPs should treat all Internet traffic equally, not discriminating based on the source, destination, or content of the data. Proponents argue that this is essential for maintaining an open Internet where all services have equal opportunity to reach users. Opponents, often ISPs themselves, argue that they should have the flexibility to manage their networks as they see fit, potentially charging more for premium services or prioritizing certain types of traffic. Without net neutrality rules, ISPs could, in theory, throttle or block access to certain websites or services, particularly competitors to their own services. They could charge content providers for faster access to customers, creating fast lanes and slow lanes. These practices could change the nature of the Internet, making it less open and more controlled by a few large companies. The debate continues in many countries, with policies varying widely. As you rest, imagine the network connections flowing through your neighborhood, the cables running beneath streets and hanging from poles, all converging on equipment cabinets and central offices. Imagine the routers and switches humming quietly, directing traffic between customers and the wider Internet. Imagine the agreements and interconnections between ISPs, the transit links and peering points, the layers of networks carrying your data from your home to destinations around the world. Your ISP is the bridge between your local network and the global Internet, the company that makes it possible for you to connect, to browse, to stream, to communicate. It's a business built on infrastructure, on maintaining connections, on providing a service that has become essential to modern life. We've explored the components of the Internet, the cables and data centers, the routers and protocols, the DNS and ISPs. Now let's watch how all these pieces work together, following a complete journey from a user's request to the response they receive. Let's trace what happens when you load a web page, step by step, from the moment you type a URL to the moment the page appears on your screen. You're sitting at your computer, and you open a web browser. You type www.example.com into the address bar and press Enter. This simple action sets off a complex sequence of events involving dozens of systems and millions of bits of data. The first thing your browser needs is the IP address of www.example.com. It can't connect to a server using just the domain name, so it initiates a DNS query. Your computer sends a UDP packet to your configured DNS resolver, typically a server at your ISP. The packet travels from your computer to your home router, which uses NAT to replace your computer's private IP address with the router's public IP address, then forwards the packet to your ISP. The packet travels over your connection, whether that's cable, DSL, or fiber, to your ISP's network. There it reaches a router that examines the destination IP address, the IP of your ISP's DNS resolver, and forwards it to that server. The DNS resolver receives the query, checks its cache, and if it doesn't have a recent answer, begins the lookup process we described earlier, querying root servers, TLD servers, and authoritative name servers until it obtains the IP address of www.example.com. Let's say the IP address is 192.0.2.1. The DNS resolver sends a response packet back to your computer, again traveling through your ISP's network and over your connection to your home router, which uses its NAT table to determine that the response is for your computer and forwards it there. Your computer's network stack delivers the response to the browser, which now knows the IP address it needs to connect to. Next, the browser needs to establish a TCP connection. Remember the three-way handshake. SYN, SYN-ACK, ACK. Your browser constructs a SYN packet, a TCP segment with the SYN flag set, indicating a request to open a connection. This segment is placed inside an IP packet with 192.0.2.1 as the destination address and encapsulated in an Ethernet or Wi-Fi frame. The frame is transmitted to your router. Your router decapsulates the frame, extracts the IP packet, performs NAT, replacing your computer's private source address with the router's public address and noting the connection in its NAT table. It then consults its routing table to determine where to send the packet. The default route points to your ISP, so the router encapsulates the packet in a frame appropriate for its connection to the ISP and transmits it. The packet arrives at your ISP's edge router, which decapsulates it and examines the destination IP. The router consults its routing table and sees that 192.0.2.1 is not in the ISP's network. It forwards the packet to one of the ISP's upstream connections to its transit provider. This forwarding might involve several more hops within the ISP's network, through aggregation routers and core routers, each one making forwarding decisions based on its routing table. The packet leaves your ISP's network and enters the transit provider's network. Here it might pass through multiple routers, following the path of BGP routes toward the destination. Each router along the way decapsulates the link layer frame, examines the IP header, decrements the TTL, consults its routing table, chooses the next hop, and encapsulates the packet in a new frame for the next link. The packet might cross an ocean via a submarine cable, might pass through an internet exchange point where networks peer, might traverse multiple AS boundaries as it hops from one ISP to another. All the while, the IP header remains largely unchanged, carrying the source and destination addresses and guiding the packet toward its destination. Eventually, the packet reaches the network where 192.0.2.1 resides. This might be the network of a hosting provider or a content delivery network with servers distributed around the world. The packet is delivered to the specific server with that IP address. The server's network interface receives the frame, decapsulates it, and passes the IP packet to the operating system. The OS decapsulates the packet, extracts the TCP segment, and delivers it to the appropriate application based on the destination port number, which for HTTP is typically port 80. The web server software receives the SYN segment and responds with a SYN-ACK segment. This response follows the reverse path, traveling back through the Internet, through routers and ISPs, across cables and links, until it reaches your router. Your router uses its NAT table to determine that the SYN-ACK is for your computer and forwards it there. Your computer sends an ACK segment back to complete the handshake. Now a TCP connection is established, and data can flow in both directions. Your browser constructs an HTTP GET request, asking for the web page at www.example.com. This request is a string of text, something like get HTTP1, 1/I RIN host, www.example.com RRNNRN. The browser hands this to the TCP layer, which breaks it into segments, though in this case it's small enough to fit in one segment, adds TCP headers and passes them to the IP layer. IP adds headers and passes the packets to the link layer. The packets travel the same path as before, from your computer to your ISP to the transit provider, and eventually to the web server. The web server receives the HTTP request, processes it, and generates a response. The response includes an HTTP header with metadata like the content type and length, followed by the actual content of the web page, which is HTML code. This response might be several thousand bytes or more. TCP breaks it into multiple segments, each one fitting into an IP packet. These segments are transmitted back to your computer. As the segments arrive at your computer, TCP reassembles them in order, even if they arrived out of order, using the sequence numbers in the TCP headers. It acknowledges each segment, sending ACK segments back to the server to confirm receipt. If any segment is lost during transmission, TCP detects this and requests retransmission. Eventually, all the segments arrive, and TCP delivers the complete HTTP response to the browser. The browser parses the HTML, rendering the structure of the page. But the HTML might reference additional resources, images, style sheets, JavaScript files, all of which are hosted at URLs specified in the HTML. For each of these resources, the browser repeats the process. It might be able to reuse the existing TCP connection if the resources are on the same server, or it might need to establish new connections if they're on different servers. For each resource, DNS lookups may be needed if the resource is on a different domain. More HTTP requests are sent, more responses are received, more data is transferred. Some of these resources might be hosted on content delivery networks, servers geographically distributed to provide low-latency access. The DNS query for a CDN domain might return a different IP address depending on where you are, directing you to a nearby CDN server rather than the origin server. As each resource arrives, the browser processes it. CSS style sheets are parsed and applied, determining how the page should look. JavaScript files are executed, possibly modifying the page dynamically. Images are decoded and rendered. Gradually, the page takes shape on your screen, elements appearing as their resources are loaded. Throughout this process, multiple protocols are working together. TCP ensures reliable delivery, retransmitting lost packets and keeping segments in order. IP routes packets across the network, with routers making forwarding decisions at each hop. Ethernet or Wi-Fi handles the local transmission of frames. DNS translates names to addresses. HTTP structures the request and response. And at every layer, headers are added and removed, data is encapsulated and decapsulated, all following the standards defined in TCP/IP. The entire journey from your pressing enter to the page fully loading typically takes a second or two. During that time, hundreds of packets are exchanged, dozens of network devices are traversed, multiple protocols are employed, and data travels thousands of miles, possibly across continents and oceans. The infrastructure of the Internet, the cables and routers and servers and protocols, all work together seamlessly to deliver the web page to you. Consider the scale of this. The same process is happening billions of times per day for billions of users around the world, all simultaneously. The Internet handles this load because of its design, its redundancy, its distributed nature. No single point of failure, no centralized control, just a network of interconnected networks, each one managed independently, but all following the same protocols, all speaking the same language. As you let yourself relax, let yourself marvel at this system. It's a human creation, built over decades by countless engineers and technicians, but it operates with a kind of organic complexity. It adapts, it roots around failures, it grows as new devices and networks are added. It's both fragile, vulnerable to cable cuts and equipment failures, and resilient, able to continue functioning even when parts of it fail. It's the technological infrastructure that underpins the modern world, connecting people and information, enabling communication and commerce, education and entertainment. And it all happens quietly, in the background, so reliably that we rarely think about it, so quickly that we barely notice the journey our data takes. As the journey comes to a close, as the web page finishes loading and settles on your screen, the Internet returns to its patient waiting. Somewhere a router is forwarding packets. Somewhere a DNS resolver is answering queries. Somewhere a server in a data center is responding to requests. And somewhere a cable lies on the ocean floor, light pulses traveling through its glass core, carrying conversations between people who will never meet the infrastructure that connects them. You can rest now. Let your breathing slow. Let your thoughts drift. The Internet will continue its work without you, this vast, intricate system humming along, connecting the world one packet at a time. And when you wake, it will still be there, ready to connect you once again, ready to carry your messages and your searches and your requests, ready to bring the world to your fingertips. If you're still awake and enjoyed learning about how the Internet actually works, consider subscribing for more peaceful journeys through the technology around us. Sweet dreams.